Hello and welcome to Arlington High School's Math 4 Honors. My name is Kirk Weiler, and today we're doing Unit Number 1, Lesson Number 1, so the first lesson of the Math 4 Honors curriculum. I'm excited to see you. I'm excited to have you in my class. I hope that you stick with me throughout all the lessons that we do and all the units that we do. It's an exciting course, it's a challenging course, but it's one well worth taking. So let's get right into it. Unit 1, Lesson 1, the rational numbers and their subsets. Really, in a certain sense, all of mathematics comes from the idea of numbers, and numbers have been around for thousands upon thousands of years, much longer than really even recorded history, which makes you wonder how we know they've been around. But literally, bones have been dug up in Africa that have shown numbers inscribed on them, I think dated to about 50,000 years BC, so a long, long time ago. So what we're going to do today is we're going to talk about some of the most common types of numbers, the sets of numbers, and some other ideas associated with them. Quite frankly, one of the most important sets of numbers, and one that students learn about very early on, are what are known as the set of integers. All right? When I talk about an integer in class, I need you to immediately know that we're talking about the whole numbers, including the negatives. All right, so all the way to negative infinity, all the way to positive infinity, but only whole numbers. In higher level math, it's important to know the symbols, the technical symbols that mathematicians and engineers and others use for these common number subsets. Strangely enough, for the set of integers, we have a symbol that kind of looks like a capital Z, but with a double strike through. Sometimes that'll be called a double strike. You don't need to know that term, but you do need to know the symbol. All right? Now, a set of numbers that is commonly associated with the integers are what are known as the natural numbers. All right? The natural numbers are the positive integers, 1, 2, 3, 4. There's some debate about this, but the number 0 is not typically thought of as a natural number. Most kids, when they first think about numbers, don't really think about 0 very well. The natural numbers are, conveniently enough, expressed with a double strike n for natural, or one of my favorites is the same symbol for integers, but with a little plus superscript telling us that they're positive. Okay? Now, in these videos, what's going to happen is when I fill up a screen, every once in a while I'm going to pause to let you write down anything on the screen, and then I got to clear out the text. All right? So I'm going to pause the video now. Write down anything you need to, then I'm going to scrub out the text. All right, here it goes. Let's move on to the next page. All right, so one of the very important ideas when it comes to sets is what's known as the closure of sets. And this is really kind of a neat idea. You see, numbers, like integers or natural numbers, or any of them that we deal with, are collections of things. But once we collect these things, then we start to put them together with various operations, the most common of which being addition, subtraction, multiplication, and division. Now, if we take two numbers in a set, and we put them together, let's say with addition, we can ask, will we get another number in that set? If we always get another number within the set, then we say that the set is closed. All right, we say that it's closed. Kind of makes sense. It means we don't have to go outside of the set to find a number that is the answer to our problem. All right, so closure means that every time you take two numbers from a set, they can even be the same number. Okay, that's important. You put them together with some kind of an operation. That operation will be specified. If the number that you get from putting those two numbers together always still lies in the set, then we say that the set is closed. All right, so take a look at the first problem on this. Exercise 2 says of the four standard binary operations, binary meaning two numbers, right? Two numbers. Of the four standard binary operations, addition, subtraction, multiplication, and division, which would the set of natural numbers be closed under, and which would not? Pause the video right now, take up to 5 minutes to think about this. If you need to, rewind the video to listen to me talk about closure again. But pause the video now to think about this. All right, let's do it. Well, the first thing I might want to do is really just kind of make sure that I remember what set I'm dealing with. Z plus is the set 1, 2, 3, 4, etc. All right, well, let's play around with addition. If I grab two sort of natural numbers at random and I add them, 3 plus 4, I get 7, and 7's in there. You know, if I do 5 plus 1, 6, that's in there. Even if I grab two of the same number, 1 plus 1, 2, that's in there. So definitely closed. All right, let's try subtraction. You know, if I do 8 minus 5, that's 3, and that's in there. If I do 7 minus 1, that's 6, that's in there. And if I do 2 minus 8, that's negative 6. Oh, no, that is not in there. It only takes one, so it's not closed. All right, let's play around with multiplication. All right, with multiplication, let's think about this. I don't know, let's do 3 times 5. We'll get 15. That's in there. How about 1 times 1? We always want to consider this case where we pick two of the same numbers. That's in there. 8 times 2, that's 16. That's in there. Yeah, okay, it's closed. All right. And division. Well, let's see. Let's do 24 divided by 2. That's 12. That's in there. 8 divided by 4. That's 2. That's in there. But 3 divided by 6, that's 1/2. Oh, no, that's not in there. No. No, so not closed. All right, so the natural numbers, i.e. the positive integers, are closed under addition and multiplication, but not closed under subtraction and division. All right, I'm going to give you a second to write down anything on that page. Okay, I'm going to scrub out the text. Next page. Well, actually, not next page, next problem. Exercise 3 says, if we now open up ourselves up to the set of all integers, under which of the 4 operations is the set not closed? Support your answer with an example. So now there's only one operation that's problematic. Pause the video, think about which one it is. All right, let's talk about it. Remember, last time subtraction was a problem, right? But now we're dealing with all of the integers, -3, -2, -1, oops, 0, 1, 2, 3. And now subtraction's no longer a problem, right? Because if I do 2 minus 5 and get -3, well, that's in there now, right? So now we're going to be closed under subtraction. We're still closed under addition and multiplication, but division is still a problem, right? Because we'll do 2 divided by 8, we'll get 1/4. We don't even have to do smaller divided by larger, right? We could just do 5 divided by 3, and we get, 5/3, or, we get 1 2/3. That's not in there, right? So still not closed. Now, the reason that we want to talk about closure is that closure really gives rise to new types of numbers. In other words, there's a long history in math of developing a type of number, like an integer, or forget about that, just like a natural number. Putting it together in various ways, addition, subtraction, multiplication, division, and then saying, well, wait a second. If I've got 2 minus 5, well, there is no number that I can really have that does that. So then we invent negative numbers, right? For division, what we're seeing is that on occasion when we divide two integers, we don't get an integer. We get something that is sort of fractional in nature, not quite whole. So I'm going to clear this out, copy down whatever you need to. Okay, here we go. All right. So division gives rise to a new type of number. All right, what's known as a rational number. And rational numbers are very, very important. All right, I want you to know this definition because it's very simple. A rational number is any number that can be written as p divided by q, or the ratio of p to q, where both p and q are integers. In other words, a rational number is any number that is the ratio of two integers. This set is symbolized by the Q. All right, and again, it's kind of got that double, that almost looked like, right? Almost, it's got that like double strike through again. All right, know the symbols. These are important symbols. I expect my students to know them, so make sure that you memorize them. Exercise 4 says, why are rational numbers, or fractions, as many people like to think of them, necessary from a practical perspective? So this is where I want you to really pause the video and say, well, I'm annoyed by fractions. I don't like fractions. As the old joke goes, 4 out of 3 people don't even get fractions. So the question is, well, if they're so obnoxious, why do we even need them? Anyway, pause the video now and think about that. All right, let's talk about it. I'm not even sure I'm going to write anything down. You see, we need fractions because ultimately when we measure things, measure, we decide on what represents a whole unit, right? So, for example, 1 gallon, right? 1 gallon, okay? But now we're trying to measure volume, right? Now, if we don't have any rational numbers, then what's going to happen? Well, we can measure quantities of 1 gallon, 2 gallons, 3 gallons, 0 gallons, but we can't really measure anything else, right? We can't measure anything in between. And yet volume is what's known as a continuous quantity. So we can have fractions of gallons. Now, in a certain sense, people's dislike of fractions then kind of kicks in as well. That's where you get people who say, oh, I don't want to deal with a half of a gallon, so, you know, I'll call it a half gallon. That's not a good example. I don't want to deal with a quarter of a gallon, so I'll call it a quart. Oh, I don't want to deal with like part of a quart, so I'll say half of a quart is a pint, which would be 1/8 of a gallon. Right? I don't want to deal with like anything smaller than a pint in terms of a fraction, so I'll say there's 2 cups in a pint, but then a cup is 1/16. And once you get down to a cup, then then you're going down to like half cups, quarter cups, and things like that, and you have your rational numbers again. So really, we want rational numbers so that we can quantify things that aren't integer multiples of whatever our whole unit is, right? Whether our whole unit is the mile, the gallon, the second, the meter, the cubic inch, anything like that. We want to be able to talk about quantities that aren't just integers. All right, clearing that out. Exercise 5. Explain why the integers are a subset of the rational numbers. In symbolic form, z is contained in q. All right, a subset. Let's make sure we understand that. Like, let's say I have a set of numbers, finite set. 5, -2, 1, 3, 8, 11, 15, 0. All right, a subset would be any set that is made by taking elements from this set. All right, so this, let's call this set A, let's call this set B. We would say that B is a subset of A, and a great way of thinking about it is that B is contained in A. That's not really a C, but it kind of looks like one. B is contained in A. All right, so really when we say explain why the integers are a subset of the rational numbers, what we're really saying is explain why every integer is also in the set of rational numbers. Now you've heard this argument before, I think, so pause the video for a minute and think about this. All right, let's talk about it. Let's just give an example, right? Let's talk about the number 5, right? The definition, which is clearly an integer, the definition of a rational number is it's a number that looks like p divided by q, where they're both integers. Both ints, right? So of course 5 can be also thought of as the ratio of 5 to 1. And because that's an integer, and because that's an integer, then the number 5 is also a rational number. So every integer is also a rational number. Not every rational number is an integer. So the rationals are not contained in the integers, but the integers are contained in the rational numbers. All right, clearing that out, write down anything you need to. Here we go. Always have to give you enough time to get that finger up, pause the video right before I move on. Exercise 6 is Q closed under the operation of division. So it's important to be able to read the language. When you see this, you have to know, oh, he's talking about the rational numbers. The rational numbers, right? The problem with the integers was they weren't closed under division. But let's play around with a couple non-integer rational numbers. Like, let's say we had 2/3 divided by 4/5, right? You remember little middle school tricks on how to do this? You know, I might do that. And then get 10/12, and yes, it would reduce, not that I care, but oh yeah, that's a rational number. Let me do like, I don't know, 1/7 divided by 4/7. Nah. So that would be 1/7 times 7/4, and that would be 1/4. Yeah, that's a rational number. How about 3/2 divided by 1/2? And that would be 3/2 times 2, and that would be 3. Ooh, is that a problem? Is that a problem? Oh, that's not a problem. That's an integer, right? So that's also a rational number. It's looking good, right? I mean, is there any possibility I could divide a rational number by another rational number and not get a rational number? Think about this. There is a possibility. Did you figure it out? This one's tricky. Division by 0. I mean, what would we get if we do 5/6 divided by 0? They're both rational numbers. Well, that doesn't exist. All right? Therefore, it's still not closed. If it weren't for 0, it would be closed. But the plain fact is, it's not closed because you can't divide by 0. Doesn't have to be a lot of examples that don't work. Only one, but it's not closed. All right. I want to talk just for a second before we move on about division by 0. Okay? Division by 0 is I'm going to erase the text, okay? Division by 0 is going to play a very, very important role for us in Math 4 Honors. So I need you to grapple with it right now, and mostly I need you to understand why division by 0 doesn't exist, or why, better yet, it can't give us an answer. All right? Now, in order to understand why division by 0 doesn't work, you really have to understand division. So you know, we're going to go on a little tangent here. 6 divided by 2 is equal to 3. We all know that. But we can justify it by saying because 6 equals 3 times 2. Right? We can say 24 divided by 4 is equal to 6 because 24 is equal to 6 times 4. Likewise, we can even do something kind of weird, like we can say 9 divided by 1/2 is 18 because 9 is equal to 18 times 1/2. So why is it that we can't do this? Think about this for a moment. Really pause the video and think about this. Well, I really hope you did pause the video, because I'm going to tell you the ugly truth. If you didn't pause the video, if you didn't think about it, this is going to be a really bad class for you. All right? You have to have natural curiosity at this level of math. You have to have a willingness to explore, to think, to conjecture. All right? But I'm going to have faith that you actually did it. So think about this. Well, if that was true, this is kind of like what's called a proof by contradiction, then 5 would equal 0 times that number. Or actually, let me be a little bit more consistent with what I was writing before. 5 would be the number times 0. But that's always equal to 0, and 5 doesn't equal 0. That's it. Now, one more. 0 divided by 0. This one's very special. All right? It's very special for a different reason than 5 divided by 0. Let's say you could do 0 divided by 0 and get a number. Well, that would imply that then 0 was equal to that number times 0, and that would indicate that 0 is equal to 0. Well, yes it is. So what's the number? Well, that means the number could be anything. It could be anything at all. So that means, ironically, it can't be anything. You see, when I add two numbers together, I don't get two answers. When I multiply two numbers together, I don't get two answers, right? So saying that 0 divided by 0 could end up being anything, well, that means I can't say it is anything, right? Because I'm looking for a single number that 0 divided by 0 is. Make sure you really process that conversation. Okay, I'm going to scrub out the text. Okay, it's pretty deep. Let's go on to the last problem. Can all measurable quantities be expressed as a rational number? In other words, if I go out and I figure out how much water is in a swimming pool, will the amount of water in the swimming pool be a rational number? Right? Will it be, 275 thirds of a gallon? Or, even an integer, because that's rational. So think about this. In a certain sense, what I'm asking in this question is quite deep. What I'm really asking is, are there any numbers that aren't rational? So the answer to this question is technically no. All right? And it's because some quantities are irrational. There are some quantities that cannot be expressed as p divided by q. All right? The most famous of which might be pi, but there's lots of other irrational numbers. And we're going to talk about them more in the next lesson. Okay? Here we go. Let's finish up. All right. Well, thank you for joining me for the first lesson of the Math 4 Honors course. I'm sort of hoping that none of my students were absent and had to watch it, but some of the explanations in class, which we just went through, can be very tricky to understand, especially the first time you hear them. So I encourage you, watch the videos before I give the lesson, watch the videos after I give the lesson. Obviously, watch the videos if you've been absent from class. And if you're joining me and you aren't even in my class, that's awesome too. All right, I'd love to have as many people watching this video as possible. For now, though, let me say that this has been another Arlington High School Math 4 Honors lesson. My name is Kurt Weiler, and until next time, keep thinking and keep solving problems.